Hi, welcome to Robot Simulations in Gazebo and ROS Part 1. This is just going to be a series of videos where I outline steps and improvements I've made in simulating a cart, a differential drive cart, a robot arm, and potentially even in the future a quadcopter in Robot Operating System using the Gazebo 3D Physics Simulation environment. So I'll begin the demonstration with the cart which I have set up. Now in this launch file that I've just executed, I've spawned a virtual cart in Gazebo. Right now this world is looking pretty barren, so I'll spruce it up a bit by adding some buildings for our cart to navigate around. And as of now, the robots I have in simulation are nowhere near autonomous. They require an Xbox controller to be controlled. So by pressing down on the throttle, I'll get my cart moving. I can steer it around. But what makes this extra fun is that in RViz, you actually get the simulated sensor data. So on the bottom left, you're getting the camera output from the virtual world. So you can see as I'm steering, driving around, you're straight up seeing what's at the front end of the car. And then at the center of the screen, you've no doubt noticed all these red dots, which are their graphical representation of the LiDAR data that's coming in from Gazebo. There's a LiDAR sensor I have represented by this black box here on top of the car. This thing that it's simulating LiDAR sensors spitting out laser output and getting reflections back from objects. And it's being processed and giving the user a good sense of what is going on in the environment. And in the future, I'd like to use this to implement simultaneous localization mapping algorithms, likely being done with the gmapping package readily available for ROS. And I'd also like to do some sort of image processing with the camera, where maybe I have the robot chase red objects using some basic image processing techniques. Now the way I've done this is if you go to the cart package in my code base, and I'll link to the source code actually in the video description, so be sure to check that out. I have a cart description file which contains a URDF. A URDF stands for Universal Robot Description File. And in there I specify all the links of the robot. These links are the wheels, the chassis, even the links representing the sensors like the camera and LiDAR, just for visual aesthetic, though they're not needed. And then I also specify the joints at the wheels and the controllers at the wheels, which are just the motors turning the wheels. And now for these controllers, they're meant to sort of emulate the way a DC motor or stepper motor or any other kind of motor would control wheels in the real world. So they're emulated using PID controllers in the virtual environment. And right now I've just given these PID values in this file here that are just to emulate how motors would behave, and these should be tuned at a later date, but this config file I have open here shows those values for the automobile. So I'll close that up and then show the second demonstration, which is for the robot arm. And for the robot arm, it's exactly the same thing. I've specified a series of links specifying the arms of the robot, their dimensions, their moments of inertia, their mass, etc. And then I've specified 3 different effort controllers for the 3 different motors, which you'll see once I get them set up. So each motor is controlled individually by one of the axes of the Xbox controller. It's slow at the moment, and the PID values can still take some tuning, but it gets the job done for the time being. So let's go ahead and spruce up our environment again. This time we'll add a gas station. I'll add a apartment all the way back here. And I'll put a house at the back as well. It's a bit of a quirky neighborhood, but it should help convey the idea of what these simulations are doing. So this robot arm is moving around the virtual environment. It can interact with objects as well, albeit painstakingly slow. So there, try to pick up the Coke can. Unfortunately, I don't have the friction on my gripper set quite properly at the moment, but you can see it knocked it down. And again, if we go to RViz, I've set up a LiDAR scanner. I'll make the dots a bit bigger here. I've set up a LiDAR scanner at the front of the robot arm, so as you're navigating it through space, you should be able to get a sense of what this scanner is picking up on in the environment. And again, at the bottom left, I have camera data specified with the camera sensor specified at the front of the robot arm. This typically isn't where you would put a camera on an actual robot arm used in industry, but I was just having a bit of fun here. So if you go back to the Gazebo simulation and zoom in on the front of the robot arm, right here I have the LiDAR sensor, and this sensor here is the camera sensor. And as you can see, when I press the Xbox controller bumper, the gripper activates, causing some kind of glitchy visuals with clipping. But that's about it for the arm simulation, and just for fun, I've also set up a very, very basic quadcopter simulation. This is going to be something I tackle far in the future, because getting the Gazebo world simulated time to sync up with any sort of controller operating at over 100 Hertz that I set up will require a lot of overhead to get those clocks to talk to each other synchronously and reliably. So right now, all I have is a plugin I've written for Gazebo to apply a force proportional to the speed the rotors of the quadcopter are going. As you see here, these rotors are really just there for visual representation. Obviously, rotors in real life look a bit different, but if I up the throttle on my Xbox controller, you'll see the drone take off. Fortunately, now it flipped, so I can't make any better demos. But that's about it for part one. Stay tuned. I plan on really improving these simulations in the future, getting these robots to behave autonomously, and hopefully even getting some good quadcopter controls going in the future. All right, thanks for tuning in, and cheers.